Okay, so we begin lecture 5 now, which is on parsing. And as usual, we would like to recap what we did in the last lecture. So, we said that it is very critical to process named entities and multi-words. They are word level processing, and they need features mostly. As opposed to generative modeling. In named entities, of course, we see HMM based processing, but a lot of algorithms make use of feature based maximum entropy algorithms. And we also discussed different types of multi-words, compositional and non-compositional. For example, white snow is compositional, white elephant is not compositional. Then we also mentioned the necessary and sufficient conditions for multi-word extraction. We have both rule based and statistical methods. Statistical methods are absolutely inevitable in multi-words because of the arbitrariness in the word combinations. We have to say many thanks and not several thanks or much thanks. There is no reason why we can't say several thanks. So, these kind of word combinations are detected by just memorizing the patterns through machine learning. Names again are of many different types, and a very important development in named entity recognition came in the form of MUC standardization, message understanding conference standardization, which proposed NMX tags, NUMEX tags and TIMEX tags. They correspond to person, organization, place names, etc. for NMX, quantities of money, distance for NUMEX, and date, time, etc. for TIMEX. So, this has been quite standardized. Again, there are rule based and statistical approaches. Statistical approaches mainly make use of MEMM and CRF, and they try to make use of features, but recently we see lot of papers on word vector based methods to do multi-word as well as named entity recognition. So, these make use of deep neural network. So, this is what was the main topic from last lecture. So, today we go to parsing, and we would like to understand why parsing is important. Parsing is probably one of the most well understood, well developed areas of natural language processing, and from parsing compiler technology has drawn lots of ideas. Many parsing algorithms are used in programming languages. So, the position of parsing is just below semantic processing and above chunking, which is shallow parsing. So, for chunking actually we tend to group together nominal categories, verbal categories and so on, and parsing actually directly interacts with semantics, because semantic relations become facilitated when we can identify dependencies, for example, and constituencies. So, what comes in front of us are sentences which have linear structure, but there is actually a hierarchy, a tree hidden behind the linear structure. Okay. And there are what are called constituents and branches. So, let me show you some very modern day applications which need parsing. Parsing is critical for these kind of applications. There is intense activity these days on metaphor detection. Okay. So, you have sentences of the following kind: the detective listened to her tales with a wooden face. Okay. Wooden face is a metaphorical combination. How can the face be wooden? Okay. She was fairly certain that life was a fashion show. Okay. The typical teenage boy's room is a disaster area. The children were roses grown in concrete gardens. waves of spam emails inundated his inbox. So, everywhere there are words which are metaphorically used. Okay. If you look at this word here, inundated, the appeal is to a wave, coming and splashing into the email box. Okay. So, there is an appeal to the image of the waves. The roses grown in the concrete garden is fine. Disaster area, here the metaphorical appeal is to a war situation, and then fashion show, of course. So, these kind of metaphorical usages need parsing, because we have to detect the dependencies. For example, if the sentence is the detective listened with wooden face, then a shallow dependency parser produces these kind of dependencies. Detective and the are related. The subject of listening is detective. Okay. Root is the root of the dependency tree. This is the output from Stanford dependency parser. Listened has a preposition with, and with has a prepositional object face, and there is an adjectival modifier wooden and face. Okay. So, the fact that face and wooden are related is important. That is, of course, captured by the dependency parser. So, getting dependencies within a sentence is a very fundamental step in language processing. Okay. A very difficult problem arises when we combine sentiment and metaphor. Okay. So, here is an example of a sentence. A well designed but not overly stylized interface makes IMDb easy to navigate, although you may find yourself going down plenty of rabbit holes, as one page of facts leads to another and so on. So, here this is a sentiment expression. Okay. So, there are positive and negative sentiments expressed here. So, for the IMDb interface, the opinion is positive, easy to navigate. Okay. But the fact that there are many linkages and you have to follow a long chain of links is not so positive, that is a negative opinion, but that is expressed metaphorically. Okay. You find yourself going down plenty of rabbit holes. So, the metaphor is for a hunting situation or exploration situation, where the explorer goes through the rabbit holes one after another, okay, and has to navigate a long path. So, this is an extremely challenging situation, and of course, NLP is trying to address this kind of problems, combination of sentiment and metaphors. They require, as a first step, dependency parsing. So, a well designed but not overly stylized interface makes IMDb easy to navigate. So, the fact that interface and easy to navigate are related is captured through a dependency parsing output. Okay. From the linear structure, this is not apparent. We need to produce dependencies. So,
why this relation auxiliary for navigator to? Who is certainly, what does it mean? Oops.
Yeah.
Had navigated, that would be auxiliary, but
yeah. Yes, I think I have to check the Stanford's output. I think I just copied it directly from Stanford output, but maybe I should check it again. Yeah. Easy to navigate. Actually, easy to navigate is an infinitive here, so I have to check it.
And what is n sub? I mean, that's wrong. N sub, easy, and IMDb.
Yeah. N sub.
IMDb is not subject of.
Where is it? N sub easy.
Interface makes, okay. So second one should be nominal subject.
Yeah.
So IMDb is not a subject of easy, right?
Yeah. Interface makes IMDb easy. So IMDb should have been.
IMDb is a object of navigate.
Object of navigate. Yes.
So
So.
two counts.
Yeah, so this is, so I need to check the output really. Okay. Then we come to the formal definition of sentiment analysis. So sentiment analysis consists of 5 tuples. Okay. So this is consisting of E, which is an entity, Aij is an aspect of entity I, Sijkl is a sentiment on the aspect A of entity E, Hk is the opinion holder, and TL is the time when the opinion is expressed. The quantity of interest here is Sijkl. So in the definition itself, we need we find that dependency parsing is needed in the definition itself. So I'll give you an example. I love the songs in the movie, though only the cast was liked by my brother, who said the director was of the opinion that the storyline, which is from a movie novel by Shakespeare, will be lapped up by the public. So it's a complex sentence, and there are positive opinions about many aspects of the movie. The entity of interest here is movie. So there are many aspects here and many people holding opinion at different points of time. Okay. And this has to be made explicit through natural language processing. So we need to identify entities and their aspects. Here the entity is movie, the aspects are song, cast and storyline. Opinion holder are I, my brother, the director and the public. Shakespeare is not an opinion holder here, even though his name appears, okay, and he is a noun. Shakespeare?
Aspect is like continuing or beginning, inquisitive or perfective, imperfective.
No, no, it is not used. It is not used in this sense.
If this time,
Yeah. No. The sentiment analysis field uses this in that sense.
But what is an aspect?
So aspect is a particular aspect of the entity. It is not the temporal aspect.
So they
Okay.
are called facets in artificial intelligence for a long time.
Yes.
65.
Yeah.
It's called facets.
Yeah, they are called facets. Yes. But sentiment analysis, the field calls it aspect now. Okay.
But it's there because aspect means something
I
very
know.
different, and you do natural language
I know.
processing. An aspect here has very precise meaning.
Yeah, I know. Yes, I know that, but I'm going by the terminology used in the field now. Yeah. And there is also a temporal issue here. I hold the opinion now. I am in the present tense. My brother held an opinion in the past. The director also holds an opinion in the present time. And the public will lap it up. Lap it up means they will almost eat it, which is in future. So if we want to create triples, okay, then it will be I love song, brother like cast, director like storyline, and public lap up storyline. Okay. So all these triples have to be detected through dependency parsing, otherwise sentiment analysis is impossible on the text. Okay. So these examples I think show very clearly that we have to detect dependencies in the text, and therefore we need parsing. What about constituency? So there is a linguistic justification for this, which the Chomskyan school of linguistics shows quite frequently and emphatically. So if we have this sentence here, the big book of poems with blue cover. Okay. This whole thing is a noun phrase, the big book of poems with blue cover. So here we have a number of modifiers for the book. The book is a big book, the is a definitive designator for the book. Of poems is a prepositional phrase, again a qualifier for the book. With the blue cover, qualifier for the book. It is, so again there is a PP attachment question. Poems do not have blue cover, the book has blue cover. Okay. Now, if we place all the qualifiers of the book, book is the head, if all the qualifiers of the book are kept at the same level, then we have a problem. Okay. So, let us say there is a sentence, the big book of poems with the blue cover is on the table. Now, there is this test called replacement test. We have one replacement, okay, which is an anaphoric replacement. I bought the big book of poems with the blue cover, not the small one. Okay. So, what does 1 bind to? What is 1 coreferential with? It is this whole phrase, book of poems with the blue cover. This, in this case, the one replacement targets book of poems with the blue cover. Another one replacement, I bought the big book of poems with the blue cover, not the small one with the red cover. So, in this case, the one targets just book of poems. Okay. So, if we have to do anaphora resolution of 1, okay, what does 1 bind to? Then we have to detect the correct constituencies. It is important to have a hierarchical structure with proper noun phrases, such that these kind of anaphoric references can be resolved. So, the parse tree indeed has the following structure. The parse tree is not a shallow parse tree. All preposition phrases are not at the same level, they are at different levels. So, book of poems forms one noun phrase, with the blue cover comes at a higher level, okay, and book of poems with the blue cover forms another noun phrase.
It could also depend on the verb, because it might be the value you pay.
Yeah.
You give a blue cover and you get the book of poems.
Okay.
See? It's like a girl in the park with a telescope. So with the blue cover could be attached higher.
Depending on the semantics, of course. So, if it was not poems, okay, then maybe this can come down, qualifying the noun here.
But I say it can go
Up also.
Under by.
Under by. Yes, yes, this is PP attachment problem. Yeah. So, this shows that the noun phrase indeed has a deep structure within it, and natural language processing applications need to respect that structure. Okay. So, so we have really two broad classes of parse trees, and parse trees of course can be ambiguous. So, just now you mentioned this famous sentence, I saw a boy with a telescope. Here we can have two parse trees. The noun phrase is I, there is no problem in that noun phrase, but in the verb phrase we can have two kinds of structure. One is V and P, where the boy has the telescope. So, this preposition phrase with a telescope qualifies the boy, okay. Or it could have another structure where with a telescope is the sibling of the noun phrase, and in this case the telescope is with me, okay. So, two different structures are possible, constituency trees. Dependency trees also can be two, therefore, because of ambiguity. So, C is the main verb, agent is I, object is boy, and with the telescope is a modifier for the boy. Okay. This is not fully developed, there are other relations in this. Or it could be.
The relation is not mod between with and the. It's what they call governor or something. The position with the noun.
Yeah.
It's not an object. That might be UNL.
Yeah. Yeah.
Not here.
Yeah. Yeah.
Surface relation is.
Right.
Okay.
Yeah. And the other kind of structure is the boy is the object and the instrument of seeing is telescope. I have the telescope. Okay. So,
Something to be mentioned here is that there is a controversy amongst linguists. So this part of dependency structures, many prefer to put telescope on top and width down, so that you might even, when you go to semantic interpretation, say that it's the case, the instrumental, deep case in this case. And so with telescope, the width actually is not there in Russian, for instance, no preposition. So many actually prefer to put the semantic head, the telescope, under so and put width underneath. It's a matter of convention.
Yeah. Okay. So this was an idea about the internal structure behind sentences, their parse trees, dependencies, and motivation. Now we go to probabilities. How do we formulate the probabilistic parsing framework? So on the previous part, is there any question or comment? Because whenever we take a natural language processing task or phenomenon and formulate the probabilistic framework, we have to understand the phenomenon very clearly. Okay. So if there is no question, then we would like to begin with the observation that probabilistic parsing critically depends on what are called tree banks. Okay. So tree banks are sentences with this kind of annotation on them. So let's say the sentence is, the campus is abuzz with new and returning students. New and returning students have come to the campus, and the campus therefore is abuzz. Abuzz means full of activity. So first level, of course, is part of speech tagging. So students are NNS, plural noun. Return is gerundial verb, and is a coordinating conjunct. New is adjective, JJ. Now these entities together form an adjective phrase, then a noun phrase. New and returning is an adjective phrase. Students with the adjective phrase is a noun phrase. Okay. With is a preposition with tag as in. So this sentence has a noun phrase, the campus, and the verb phrase is abuzz with new and returning students. Problem?
Yes, because the returning should be on the same level as the new, is it?
It is. So
no, because the end.
Yeah.
How
No.
do you present the coordination here? I think there is some
No. I did not show the whole indentation here. Okay. Otherwise, the bracketing is fine. I could have removed these also on the other side, but I did not show all the indentation. So no, I think it's okay. You can see later. So the point is,
I think it should be put under new, the first parenthesis to show, or returning should be moved twice to the right.
no, the adjective phrase consists of new and returning.
Yeah, returning should that be moved to the right.
Yeah. So this whole thing can move here. Yeah. So to show it, but the bracketing is fine.
Yeah.
The levels are not fully. Maybe. Yeah. So we have these kind of sentences and the pause tag annotation, the phrasal annotation, and the bracketing to create the training corpus for a probabilistic parser. So let's see the formulation. The formulation is a noisy channel modeling again. The source sentence comes on the input side. On the output side, we have the target parse. Okay? And we have the noisy channel metaphor. We are very familiar with this by now. T star, the best possible tree, is the one whose probability is the highest given the sentence. Okay? So argmax over T, Pt given S. Now I apply Bayes theorem, get Pt into Ps given T, likelihood probability, prior probability. Now something very interesting happens. Unlike part of speech tagging, this part, the likelihood part, can be dropped. Okay? In part of speech tagging, this was word sequence and this is the tag sequence. Here this is tree and this is the sentence. If for part of speech tagging we could not drop it, for parsing we can drop it, because given the tree the sentence is unique. Okay. So, the probability of the sentence given the tree is absolutely certain and this value is equal to 1. Okay. So, that is an important observation for argmax based computation of natural language processing. Okay. So, only few applications in natural language processing enjoys this happy situation, that the likelihood probability does not come in the parameterization. Okay.
Yeah,
so,
but if you want to produce abstract trees,
then
it's not the same anymore.
Abstract trees, yeah.
You suppress articles, you put articles into variables, etc. You move things around to normalize the order. In that case, you
if
have to take this into account, and that's our problem with Ritesh, right?
Yeah. If T is abstract, you mean T is an abstract tree. Yeah, yeah. So if T is a constituency or dependency tree, then there is no problem. Yeah.
Projective constituencies.
Yeah. So we have argmax PT over all possible T. Now this is a very interesting situation. The best possible T is the one whose probability is highest, of course.
I have a question here.
Yeah.
Always you say the best V maximum.
Yeah.
There may be many trees that actually have the same probability.
Yeah.
You want one of them.
Yeah.
Or you have to have some kind of rule to say which one you prefer. If they have the same probability or frequency, in a way, I mean, whatever, the same score, say. You cannot guarantee that only one has a maximum score.
Yeah.
Usually several have a maximum score.
Yeah. So in case of entities with the same probability value, you resolve the tie arbitrarily, choose one of them. Okay. So if a sequence has multiple parts of speech and all the parts of speech sequences have same probability, you choose one of them arbitrarily. Okay. But in this case, also if many parse trees have same probability value, then you choose one depending on maybe the size of the parse tree. I don't know. Okay. But yeah, this is valid, of course.
The size would be the same, but maybe the geometry, the deepest or the shallowest or things like that, no?
Yeah, or you have to invoke some amount of semantics maybe. Yeah. Okay. So this is the formulation, and now since we have gone through part of speech tagging already, we have to think of how to get the best possible tree, okay, efficiently. That old question comes in now, and we will see the formulation for this as we go along. So at this point, it is interesting to discuss the probability of a sentence, which is also called the language model. So the frequentist approach is the probability of a sentence is the number of times the sentence appears in the corpus divided by total number of sentences in the corpus. Okay. But of course, this will many times lead to 0 probability, because a sentence has a very low chance of appearing as such in the corpus. Okay. So what we do is that we divide the sentence into small parts. We take an n-gram based approach, for example. So we get the probability of a sentence as the product of probabilities of n grams, which is the language modeling approach. If we have bigram assumption, then we have probability of wi plus 1 given wi, the product. If you have more information, if you have annotation, for example, so if we have part of speech tagged corpus, then the probability of a sentence we have seen is given by the joint probability of the sentence with the tag. Okay. And this is equal to the joint probability of the present tag and subsequent tag, the bigram probability on the tag, multiplied by lexical probability, the current tag producing the current word. Okay. And this is equal to the probability on a hidden Markov model, state to state probability with the symbol. Okay. So, this simply becomes the probability of a path which the sentence represents. Okay. So, this is different from the word based language modeling probability. If we have the parse tree, then something interesting happens again. The probability of the sentence is probability of the sentence with all its possible parse trees. Okay. This is the marginalization over all possible trees. Then probability of W and TR is probability of TR into probability of W given TR, which is nothing but probability of TR. So, the probability of a sentence is the probability of is the sum of probabilities of its parse trees. Okay. So, there are three different approaches to get the probability of a sentence. It depends on the amount of annotation we have. Okay. So, it is either product of bigrams or product of transitions in a hidden Markov model, or the sum of all possible parse trees. Which language model is better? Intuitively, possibly this will be the best, okay, because this has the maximum amount of information, possibly. Now, what is the meaning of best? The meaning of best is it should be able to give the probability of well constructed sentence and score a set of sentences very well depending on their plausibility, or it should be able to produce the next word given a sequence of words. Okay. So, which approach has better modeling or better predictive power depends on our annotation availability. Okay. So, it is useful to remember this. Let me just say this once again. The probability of a sentence can be modeled either by n-gram probabilities or by path in an HMM or by sum of its parse trees.
How do you define the probability of a parse tree given the fact that
you
have no grammar here, but then the things you observe have unit rules.
Yeah.
So the degree of ambiguity could be infinite.
I am coming to that.
Yeah. So how do you define probability of a tree?
I am coming.
Or in a collection of trees?
Yeah, I am coming. Coming to that. So, the probability of a sentence has great usages. We can make use of probability of a sentence to decide the quality of translation output. We can use it for natural language generation. We use it for automatic summary generation, speech to text and text to speech, okay, that is next word prediction. All these very important applications have to make use of probability of a sentence. Okay. So, now we would like to understand this quantity, the quantity probability of a tree. How do we get the probability of a tree? So, that requires something called probabilistic context-free grammar. So, probabilistic context-free grammar is just like a context-free grammar. It has a set of terminals, a set of non-terminals, a special symbol which is the start symbol, a set of production rules, context-free rules, and a set of probabilities which come with the rules. Okay. So, this is the probabilistic context-free grammar. This is context-free grammar with probabilities. The rule probabilities have to obey the law of probability. So, for example, if noun phrase goes to determiner and noun, if this has a probability of 0.2, noun phrase goes to noun has probability of 0.5, noun phrase going to noun phrase followed by preposition phrase has probability of 0.3, then this is a legal probability distribution. All these adds up to 1.
So,
Yes.
traditional stochastic grammars,
Yes.
Salomar, for instance.
Yeah.
Actually, you have probabilities for the right-hand side of productions with the same symbol on the left.
Mm-hmm.
That is NP.
Mm.
You have 3 rules.
Yeah.
Okay, but now over the whole grammar, you have nothing.
Yeah.
Okay.
Yeah, that's true. It is only for a single non-terminal.
Okay.
Yeah. Okay. So what does this? What do these numbers mean? 0.2, 0.5, 0.3. So NP goes to DTNN. Probability 0.2 means 20% of the training data parses use the rule NP goes to DTNN. So if we look at the annotated corpus of bracketed sentences, then we will see that 20% of those sentences are marked as NP DTNN amongst all noun phrases, noun phrase marked sentences. 20% of them have DTNN as the right hand side.
Okay, that's sentences contain several noun phrases. So
Right.
here, it's not very clear whether you count simply the number of sentences where this rule happens in the tree, or whether you count the number of subtrees, nodes of parse trees, that have NP and 2 nodes, DT and N under them.
Yes.
I would rather say the second one.
Second one is the one. Yes.
Yeah, so it is not the percentage of number of sentences.
No, no, not the sentences. Means 20% of
the percentage in the forest consisting of all the trees.
Right.
Percentage of subtrees of phase 1.
Yes.
That are of that form.
Right. So amongst all those subtrees whose root is NP, 20% have these as the leaves, DT and N. Yeah. So here is a probabilistic context-free grammar. We have the lexicon here with probability and the syntax here again with probability. So the lexicon is very simple here and very artificial. DT goes to the, NN goes to gunman, NN goes to building, VBD goes to sprayed, NNS goes to bullets, and preposition goes to with. Okay. And assuming there is no other preposition, P goes to with must have probability 1.0. Okay. The NN probability is divided into 2 parts, 0.5 and 0.5 for gunman and building. And the syntax is sentence goes to noun phrase, verb phrase. Noun phrase can be of 3 kinds, DTNN, NNS and NPPP. Preposition phrase is 1, P and NP. VP again is of 2 kinds, VPPP and VBDNP. So this is the grammar and this is the lexicon. This surely can produce ambiguous parse trees. Okay. So we take this sentence here. The gunman sprayed the building with bullets. The gunman sprayed the building with bullets. The question is, with bullets should be attached to what? The building or the gunman?
Why do you choose Chomsky normal form grammars?
Because
we were known to give more precise, more ambiguities than say flatter.
Yeah.
So why do you do that?
Because it is linked with the CYK algorithm, and that algorithm is used for probabilistic parsing.
Yeah.
I mean, there is also a grammar for Greibach normal form, algorithm for Greibach normal form, but that is more complex. This is directly amenable to probabilistic CYK. So,
but then it does not correspond to natural grammars. And for arbitrary grammars, you have the early algorithm can be amenable to probabilistic parsing as well.
Yeah.
And it takes any grammar, not Greibach normal form,
Absolutely.
not Chomsky normal form,
Right.
but any kind.
Yeah. But I've chosen this for illustrating the concepts. It is easy for teaching actually. So this particular sentence has 2 parse trees, VPPP with bullets. So in this case, the VP has VBD, the building, and bullets is with bullets is here. So, this means that the with the bullets is attached to sprayed. The other parse tree possible is the building with bullets. In this case, the building has bullets, though semantically that is odd. So, this is the other parse tree. Okay. In one case, with bullets is attached to building, the other case with bullets is attached to sprayed. So, semantically which is more viable? Semantically, I think it makes sense to say that the gunman, since the gunman is the agent and he used bullets, so spraying must be with bullets. So, with bullets is attached to sprayed. That is a more viable semantic interpretation. So, let us look at the probabilities and we will see how the probabilities are computed, but let me just give you the basic idea of how to get the probability of a tree. The probability of a tree is obtained by taking product of all possible probabilities on the nodes. Okay. So, NNS going to bullets has probability 1.0 as given in the grammar. There is only one plural noun which is bullets. So, this is 1.0. NP goes to NNS has probability 0.3. PP goes to P NP, that has probability 1.0. Okay. P goes to with probability 1.0. Verb phrase goes to VP PP, this has probability 0.6. VP goes to VBD NP has 0.4. So, all these probabilities are multiplied to get the probability of the tree, parse tree. Why so? We will see very soon, but that is how the probability of a tree is computed. We will see what are the production rules which are applied on the tree and take the probability values from the grammar PCFG and just multiply them. Okay. So, if we do so, then the probability of this tree is 0.00225 and the probability of the tree which is less semantically less viable is 0.0015. Yeah.
Perhaps I'm wrong, but I have the impression it doesn't capture anything about semantics. For
No.
example, if I give a sentence like the man washed the building in glass.
Yes.
It will still give this sentence a correct
Absolutely.
higher score. So
absolutely. So, I am just mentioning semantics to say that by chance, it is by chance. It is by chance by chance that this probability is coming out to be higher. Yeah. Okay. It totally depends on the data. Okay. If in this case probably the data has more PP attachment with the verb, yeah. So the sentence has been lucky.
Yeah. I mean
it is just lucky.
Once we train a model, we
yeah.
can say that if we observe 60% and 40%, then we treat the 60%. We are quite sure that we are only about 60% right.
Yes, yes. So this for example will go wrong with the same score, same kind of scoring. The gunman sprayed the building with a lot of paintings. Okay, with lot of people, for example. The gunman sprayed the building with people. Okay. So, in this case, this kind of scoring will be wrong. So, whole thing is decided by the data, the amount of evidences you have in the data, that is all. Yeah. Okay. So, what I wanted to illustrate here was how you compute the probability and how the data decides the scoring. In this case, we have been lucky that the semantically viable parse tree has got higher probability. Okay. Now, this taking the product of probabilities, I think that reminds you of the HMM. In HMM again we take product of probabilities over the whole hidden Markov model to get the probability of the sentence, parse tree and so on and so forth. Okay. So, this is the methodology.
Well, what can be said here is that if you compute this probability, this is the probability of any derivation corresponding to that tree, in particular leftmost or rightmost, they will all have the same probability. If you simply said that one writing act by one of the rules has the probability of the rule. So that explains why you have that multiplication, right? Is probability of leftmost parses. That case, okay. Just observe, and then the mechanism can be put in action.
No, but I think we have to justify why the probability of the tree is computed as the product of probabilities of subtrees. Okay.
They are not probability of subtrees. They are simply, it is multiplication of probabilities of rewritings.
Rewritings,
that
rather.
Is of derivation.
Yeah, sorry.
This is the probability of any derivation corresponding to that tree, in particular leftmost or rightmost derivation, which people understand very well. Any derivation from the S to the frontier following that tree will have that probability. That is the meaning of the thing here.
But it is also the product of subtrees. It happens to be so. The product of this part, the probability of this part.
This is the product of PP of any derivation from the PP to with valence, corresponding to that subtree.
Yeah.
It's exactly the same. It applies to the whole to any part. Exactly.
Yeah. So.
But there is something in the theory of that you should. I don't remember the moment, but something that shows that the probability of the sentence and probability of the trees generated by stochastic grammars actually are not the same. I remember some articles, some deep article about that. But anyway, that's not the problem. This is a mechanism to write scores. What we did here, this Chomsky normal form analysis for Russian French translation in 62, we did not have that. And we were then forced to do a tournament to elicit, to produce one best tree. And tournament, you know, competition, preferences between two trees, and you go like in the tennis tournament, and then you end up with a winner. And that's very bad. Any method that can give you a reasonable score is better. Because the scores just project you on one line, you don't need to do comparisons between two elements, you see.
By the way,
that's also a practical argument.
The probability of this sentence though is 0.00225 plus 0.0015. The probability of the sentence is surely not same as the probability of the tree. It is the sum of the probabilities of all the trees.
Yeah.
Okay. So anyway, so now we come to some fundamental discussion on how to get these probabilities. So the probability of a sentence, okay, this is obtained by the analysis of what is called the domination. Okay. So the probability of a tree, okay, for a sentence is the probability of the starting symbol dominating the whole sentence. Now, domination is a linguistic term. Computer scientists prefer to use the term yield. Okay, people from parsing technology and compilers and so on, they probably are more comfortable with yield, though the linguistic terminology, more common terminology is domination. So the probability of the parse tree for the sentence is the probability of the starting symbol dominating the sentence. That means the probability of the tree having the yield as the sentence. Okay. What is the probability that this sentence is the yield of this tree produced from the starting symbol? So, probability of a sentence of course is the sum of the probabilities of its trees. Now, there are three important assumptions in the probabilistic context-free grammar. The first is place invariance, the second is context freeness, and the third is ancestor freeness. It needs a bit of thinking to see why all the three assumptions are needed. Maybe we can take this as an exercise to see that all these conditions are independent, they are all needed really. Okay. So, first is place invariance. The place invariance assumption says that the probability of a rewrite rule is same anywhere in the parse tree. Okay. So, if the production rule is applied here, whatever probability it has will not change if the production rule appears here. Okay. So, all the production rule has place invariance, the probability remains the same wherever it is applied. The second is context freeness. This applies to the siblings. Okay. So, the probability of this subtree is not affected by any of its brothers or sisters around it. This is context freeness. And the ancestor freeness assumption is that the probability of a subtree is independent of any of its ancestors' influence. Do we need?
There is also one thing to see here.
Yeah.
That you need to have independent rewritings. That is, if you would use grammars with parallel rewriting, or matrix grammars, or program grammars, etc., then we could not apply that, for instance. So, if we would have to apply the rule at all possible places where it is applicable in a derivation, then you lose that those independence properties. And for instance, if you have S give SS or A, and if you ask for parallelism, you will generate A to the power 2 to the power n, which is clearly non-context free.
Okay. Yeah. So, these assumptions now give us a way of computing the probability of a tree. So, the probability of a parse tree is the probability of domination. We say that Nj dominates from k to L, symbolized as NKLJ, if WKL is derived from Nj. Okay. So, take a sentence and take the words k to L, word number k to word number L, and if Nj produces this segment of the sentence, okay, then this Wk to Wl is the yield of Nj. So, the probability of a tree given the sentence is the probability of the tree being generated from the start symbol S, and S dominating from 1 to L. 1 is the starting word, L is the last word. So, the probability of S dominating this whole region is the probability of the tree. Okay. So, then since we are working with probabilities and working with statistical NLP, we have to have a way of converting these large probability into small probabilities and combining them. Okay. So, Pt given S approximately equals joint probability of constituent non-terminals dominating the sentence fragments. Okay. Here is an example to do this. So, the probability of this whole tree is probability of the tree given the sentence, which is the domination probability 1 to L. Now, what I do is that I apply chain rule. Okay. So, this tree, the probability of this tree is the probability of domination of different non-terminals and terminal symbols. Okay. So, the probability of tree is probability of NP dominating 1 to 2, this area, probability of DT dominating 1 1, that is a single word, probability of VP dominating from 3 to L, and so on. Okay. So, the probability of tree is probability of joint domination. Now, I apply chain rule and the independence assumptions. Okay. So, this is only one step of the derivation. So, this is probability NP12, probability NP12 and VP3L given S11, probability DT11 N22, NP12. Okay. So, NP12 has come here. Now, if the question is what happened to S11, okay, S11 disappears because of ancestor freeness assumption. Okay. So, probability of DT N22, this one is dependent only on NP here and nothing above in the tree, and also nothing in the context. It does not depend on the sibling, it does not depend on the ancestor, it depends only on its own root. Okay. So, context freeness, ancestor freeness assumptions, let us drop this symbol and this symbol also. Okay. Both VP3L and S11 drop. S11 drop because of ancestor freeness, VP3L drops because of context freeness. Okay. So, if we apply the chain rule repeatedly and make these independence assumptions, we get the probability of the tree as the probability of these dominations or rewrite rules finally.
No, as a product.
Okay. So, the probability of the tree is first the probability of this, which is the probability there, then probability of this, probability of this, probability of this, probability of this, and so on. Yeah. Probability of what? Is not written here? Yes. So, as I said, you have these collected here. Now, NP12 and VP3L comes from here, S11. Now, the chain rule would demand that NP12, VP3L and S11 all these appear here. Okay. They will appear, but after that we will make use of context freeness assumption. So, VP3L will drop from the conditioning part. Okay. And then we will apply ancestor freeness assumption. S1L is the ancestor of NP12, that will drop here. So, I have omitted some steps here, okay, and said that using the
Which VP3L will disappear? It's at two locations in the formula. Okay, so
VP3L is appearing once here.
what is the final result? The one after the equal sign?
Yeah, this one.
Okay, so here VP3L etc. does not disappear, it is there.
No, it disappears from the conditioning part. It comes in the, of course, it comes in the.
No, it has disappeared. We understood that it will disappear from the second occurrence. I understood that it would disappear later. No, this is the final result.
Yeah.
In case I agree.
So, VP3.
This is the result of computation, right?
Yeah.
Okay.
Right.
Then you have already done everything you could.
Yeah. Many steps are omitted here.
Okay, okay. But this is the final result.
Yes.
I think it's okay.
It is okay, yes.
But I understood that you would further eliminate things from that formula.
No, no, nothing else will be eliminated from here. Yeah. Okay.
No, it has very nice form actually.
Yeah. So it is the product of all these things. Yes. So this applies repeatedly, the chain rule and independence assumptions. Okay.
Actually, you can simplify this by simply equating that with the product of the probabilities of the rules you can see on the tree.
Yes.
This is the first one is probability of the rule S gives NPVP.
Yes.
And second one of the rule whatever.
NP goes to DTNN.
Yeah.
These are all product
It's
of rules.
exactly probability of the rules applied in the
Yeah,
tree.
exactly.
So again, of a derivation of the yield of the tree from the start symbol.
Right. Yeah.
Same formula.
Yeah. So this has a nice interpretation, and many times I find that my students appreciate a particular analogy. So if I look upon S as the Prime Minister, then S is the Prime Minister, NP and VP are two chief ministers, and these are maybe state ministers, these are the leaders in villages, and so on and so forth. Okay. So that domination by king or the president is possible, or the prime minister is possible, if all the chief ministers and state ministers, they dominate properly. Okay. This is a product of that domination. So the product is important here. Now we can do the same thing for probabilistic dependency trees. We can make use of the theory of probabilistic context-free grammar, and then have an equivalent theory for probabilistic dependency grammars, okay, PDGs.
But there is no, in dependency trees, there are no S and no non-terminals. So
in dependency trees?
no, there are no non-terminals.
There are no non-terminals, but there is a tree surely. The root is the tree of the whole sentence, and after that you begin to have dependencies in the form of trees.
Probability of different non-terminals.
Okay.
I mean, that part has been maybe should be erased, or it comes from the other slide.
Yeah. The probability is the probability of that comes from the other side. Yeah, this should be erased. Yes, correct.
It's rather the probability of the different arcs. Right?
Yes. Yeah. Probability of different arcs, but the concept of domination is there. An arc covering a particular part of the tree, part of the sentence.
No, a node, of course. An arc does not cover a part, but the node covers. A node is a root of a subtree consisting of that node and all the nodes below, and it is exactly the same notion of yield.
No. Let me come to.
An arc does not.
No, let me come to the dependency tree. There is for projective dependency trees, you have the concept of an arc covering the whole segment.
Well,
let me come to that part. Okay. So now something to think about here. Where is the fallacy? So there are problems with probabilistic context-free grammars. If you think about it, consider a grammar S goes to ASB, and the probability of this rule is 0.7. S goes to epsilon, the probability of this is 0.3. So this context-free grammar generates this language: epsilon AB, A square, B square, A cube, B cube, A and B n, and so on and so forth. This is an infinite language. Now, given A square, B square, you have this tree here. S goes to ASB and ASB epsilon. So this probability is 0.147. Okay. So given this string, you have only one parse tree possible. This is the parse tree. Okay. And the probability of this parse tree is 0.147. What happened to the rest of the probability? 0.853. Who has eaten up this probability? wrong ones?
But the other strings, of course. Epsilon has 0.3 from that. AB has 0.21, etc. And then the sum from 3 to infinity will adapt to this.
No, but given this string, we have only one tree possible, no? As far as the grammar is concerned.
Yeah.
So, what happened to? So this should have been 1, isn't it? Because there is only one tree possible for this string. Okay, just one more example.
Yeah, I see. This is because, as I said, there's this problem that is not really a probability. Yeah.
Not a probability?
No, it doesn't take it into account the other possibilities. Here, this is related to the whole language. Okay? But the probability of a derivation here is just what you said, probability of that derivation. Okay?
Okay.
With respect to all other possible derivations, not only to those concerning A2, B2. That is the meaning of the stochastic rewriting, right? And when you write on the condition on AB, here there is a problem. It starts from here.
So this has two parse trees. Okay, AB has two parse trees. One is this, the other is this parse tree. Now, of course, the grammar is a bit different, ASB, AB and epsilon. Again, the probability of the rules is summing to 1, that's fine. And given
no,
A.
But the parse tree here, it's wrong up there. It has two daughter nodes, one A and one B.
No,
Yes.
only AB.
For S gives AB, there are two daughter nodes.
Okay.
A and B.
So A and B, okay.
There's a mistake here.
Yeah, anyway, but the probability is 0.2. And the other possible parse tree is S goes to A, S and B, S goes to epsilon. Now this is 0.7 into 0.1, probability is 0.27. What happened to rest of 0.73? So you are saying that wrong parse trees eat up the rest of the probability?
It's the same idea as
It's about it.
Christian suggested. Because that's stochastic. It's like we are considering that the determinant. I can see in this example the determinant the can be a verb, which is never possible, but we still consider it because it's a part of the grammar. I don't know why.
But AB can produce other parse trees, you think, other than these two? You have to follow the grammatical rules.
No.
Yeah.
Just because grammatical rule. Yeah.
So I don't see how AB can produce any other parse tree.
No,
It can't. But still, the other parse trees will consume probability.
What is wrong is to say that it is the probability of T condition on AB.
But that's how the tree is defined.
It's not the same interpretation of probability as you had before, which is probability in a distribution of strings and parse strings. Okay, if you take this seriously, probability of T or certainty that T is the tree for AB, of course it is 1. Okay, but this is not anymore a real probability. And this is my objection, you see, at the beginning when you say, okay, we are in probability, we make as if the things would be not related, and we are in a probabilistic space. Well, that is not the case. Because here, the T's, etc., and the strings are very much interrelated. They are not independent. To the point that there is exactly one tree or one possible string here. So there is no independence at all.
So if you
no independence at all. So the very axiom assumption people start from is simply wrong in that case.
So actually, there are 2
They
points
should
here.
be events of the same kind.
Yeah.
They are not.
So
they are totally interrelated. You have the tree, you have the string. You have the string, you have the tree. They are not independent. They are absolutely like one dependent. That's why it cannot be. Can you choose this conditional thing?
So, you see the probability of a tree given a sentence is linked with the probability of domination. Yeah.
I have the impression that here the probability that on the right is the probability of AB and not the T conditional AB, right?
Yeah. Because they are the same. This T and AB are the same object. So you cannot say this condition, it's wrong. It's the same thing, because they are highly dependent to the point they are one-to-one
Here
dependent.
is 1 to 2, but still.
1 tree, for here.
The probability of this is the probability of the sentence, you mean, probability of AB.
Yeah, we can of course calculate the P of a certain parse conditional on AB, and it would be normalized and it would be go all right.
Will it be? Okay. Then it should have happened in the last case also. There is only one parse tree.
Yeah.
So
So this is the probability of the production A square B square, and it is this. If we calculate the P of this parse conditional on A square B square, it will be 1, right? Because we just do normalization and it will be 1 anyway.
how? Maybe we should talk after the class about this. It's not. I do not see that happening here. Okay. Okay, we'll talk about it. Okay. So now we come to the question of computing the parse trees. Okay. So how can we compute the parse trees? There is a lot of similarity between probabilistic context-free grammar and hidden Markov model. O is the observed sequence in case of hidden Markov model, and the sentence is equivalent to that in the probabilistic context-free grammar. The state sequence in hidden Markov model corresponds to the parse tree in the probabilistic context-free grammar, and the model in HMM corresponds to grammar in PCFG. This is the correspondence. And then there are these three fundamental questions. In HMM, we ask how likely is a certain observation given the model, how likely is a sentence given the grammar. Okay. This corresponds to forward backward probability. How to choose a state sequence which best explains the observation, how to choose a parse tree which best supports the sentence, and the last question of course is how to choose the model parameters that best explain the observed data. This is the Baum-Welch algorithm in HMM. How to choose rule probabilities which maximize the probabilities of the observed sentences. Okay. So, this is the Baum-Welch equivalent of PCFG, probabilistic context-free grammar. This is the Viterbi equivalent of PCFG, and this is the forward backward probability calculation of HMM corresponding to PCFG. Okay. So, now why we have to think of these possibilities? The reason is that the probability of a sentence is sum of its probabilities of parse trees. Okay. The probabilities of the parse trees have to be summed together. So, this should be done efficiently. We should be able to use dynamic programming, so that the probabilities of the subtrees computed for a previous tree can be reused in another parse tree computation. So, here we make use of some interesting probabilities. The first probability is called the inside probability. Inside probability corresponds to backward probability in hidden Markov model. So, inside probability is what is the probability of having a noun phrase at this position such that it will derive the building, such that it will dominate this segment here, the building. And then there is the outside probability, which says that this is called the alpha probability. Alpha NP 45 here is the probability of starting from N1, the start symbol, and deriving gunman sprayed the building, and NP and with bullets. So, this is the probability where we start from the start symbol, get the prefix of the segment and the suffix of the segment, and the non-terminal dominating this segment. This is known as the outside probability. So, outside probability is like the forward probability in hidden Markov model. So, the random variable which is considered is the non-terminal being expanded, for example, NP, and the region in the sentence which it dominates. So, let us see how we can make use of these inside and outside probabilities. So, for this I will take an illustration. So, everything is motivated by the possibility of reusing computation on subtrees. So, if you look at this first NP, a flight, next NP is a flight from Indianapolis, next is a flight from Indianapolis to Houston, then a flight from Indianapolis to Houston on TYA, and so on. So, to compute the probability of this tree, we can make use of the probabilities which is already computed for this noun phrase, and so on. Okay. So, we should be able to make use of the work which you have already done before. So, this is the idea of dynamic programming, and very similar to what we did for forward and backward probability calculation, or even Viterbi probability calculation for hidden Markov model. So, the idea is to be able to use the probabilities already computed, that leads to efficiency. Okay. So, now we come to an algorithm which probabilistic parsing has found to be very useful. Okay. This is the CYK or CKY parsing, and this algorithm makes use of grammar, context free grammar in Chomsky normal form, where all the productions are of this form. A goes to two non-terminals, or A goes to a single non-terminal. A non-terminal goes to two non-terminals exactly, or to a terminal. Okay. So, if the CFG is not in Chomsky normal form, we can convert it into CNF by some transformation rules that is well known from the literature. So, CYK algorithm, I will first illustrate the CYK algorithm on this same sentence here. It is quite it is with an animation. So, quite nice to appreciate that way. So, the sentence is the gunman sprayed the building with bullets, okay. And it is important to see these indices. 0 is before the sentence, and between every index, so to every two index there is a word. So, 0, then the, then 1, then gunman, then 2, and so on and so forth. So, first we record the indices starting from 0, and we record the indices starting from 1 going up to 7 in the columns and 0 to 6 on the rows. So, each cell therefore is responsible for a word between two positions. Okay. So, this cell, for example, is responsible for the sentence segment which is between 2 and 3, this is between 2 and 4, and so on and so forth. Now, the CYK algorithm is quite elegant. First, we have a determiner between 0 and 1, the. Then we have between 1 and 2 a noun, gunman. Now, DT and NN together can be combined to produce a noun phrase NP02. Okay. So, the noun phrase is between 0 and 2. Now, there is a VBD between 2 and 3, yes, spread. Then we try to see if we can create bigger syntactic structures, okay, by moving up the column. So, between 1 and 3 it is not possible to create any syntactic structure. Similarly, between 0 and 3. Okay. So, VBD, then we have a DT here, the between 3 and 4, again an NN between 4 and 5, the building. Now, an NP can be found out between 3 and 5, the building is an NP, and we can get bigger syntactic structures. We can get a verb phrase between 2 and 5, spread the building. Okay. Then we can have even a sentence constructed between 0 and 5. A sentence has been found. So, you might object that why didn't you find a sentence from 0 to 3, the gunman sprayed? We did not find because our grammar did not allow a verb phrase to consist of only a single verb. Okay. It required a noun phrase. We proceed this way. Then we find a preposition between 5 and 6. We cannot compute any bigger syntactic structures here. We find a noun phrase NNS here. There is a bit of shortcut here. We actually find NNS, and then we get a preposition phrase here between 5 and 7 with bullets. Yes. Then we find an NP between 3 and 7, the building with bullets. Here bullets is attached to building. We find a verb phrase between 2 and 7, spread the building with bullets. In this case, the attachment is with bullets, with building, with bullets attached to building. Then we find a sentence between 0 and 7. This particular matrix contains the whole parse tree, and not only the single parse tree, it contains both the parse trees here. Okay. There is one verb phrase from 2 to 5, VBD 2 to 5, another verb phrase 2 to 7, okay, and then NP 3 to 7. So, both the parse trees can be recovered if we do a backtracking on the pointers from the parse tree. Okay. So, this algorithm is well known from classical parsing. What is the probabilistic version of this? So, probabilistic parse tree construction now makes use of these probability values and the inside outside probability. So, the algorithm that I will illustrate will make use of the beta probabilities or the inside probabilities. So, the beta probability is defined as recursively as the beta probability on a non-terminal is probability of a non-terminal generating the terminal given the grammar. Yeah, given the grammar. Okay. So, then the beta probability can be recursively obtained by making use of the beta probability on the terminal multiplied by beta probability on the non-terminals. Okay. So, this procedure goes, and I have an illustration here, okay, where at every cell you can record the beta probability computed incrementally, okay, and then this comes out very efficiently through the different beta probability calculations. This shows the proper beta probability. This is the probability of the tree here. Okay. So, this is fine. I will just take 1 minute to tell you about different parser, probabilistic parser comparisons that we have done. we have compared Charniak, Collins, Stanford and RASP. So this part is important because suppose you are going to buy a probabilistic parser, okay, or use it for your application. Which probabilistic parser will you use? So different phenomena are studied. So handling ungrammatical sentences. This is an ungrammatical sentence. Joe has reading the book. The parse tree is correctly produced by Charniak parser. I will go very fast over this. Please go over the slides. Collins also produces correct parse tree. Stanford produces correct parse tree. But RASP, which is the robust, accurate statistical parser, produces wrong parse tree. It is also important to understand why this is produced. Second phenomenon is ranking in case of multiple parses. So here the sentence is, John said Mary sang the song with Max. With Max is a preposition which can be bound to a lot of things here. But all the parsers, Charniak, Collins, Stanford and RASP, all of them produce correct parse tree. Embedding handling is very important. Here is a sentence. The cat that killed the rat, that stole the milk, that spilled on the floor, that was slippery, escaped. Who escaped was the cat finally. And you can see that all parse trees produce the correct parse tree. They detect the complex noun phrase and escaped. Okay, all of them. RASP actually makes it quite clear. Okay, there are complex noun phrases, embedded noun phrases. Then handling multiple part of speech tags is important. Time flies like an arrow is a very famous sentence. It has many interpretations. Charniak, Collins, Stanford, RASP. Charniak, Collins and Stanford produce the parse trees as we understand. RASP has a very interesting twist. It looks upon time flies like an arrow as a noun phrase, and that is valid. You can have a sentence like time flies like an arrow came in droves through the window. Okay? So here time flies like an arrow is a noun phrase. And then repeated word handling is our famous sentence, buffalo, buffaloes, buffalo, buffaloes, buffalo, 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 etc., 7 buffaloes. So all of them go wrong, and RASP just gives up and makes all the buffaloes at the same level, below one noun phrase. But we know that the correct tree is this. Okay, this requires semantics. So another sentence of same structure is brown cows, black cows, cow, cow, white cows. Cow means to intimidate. And then what about long sentences? Many times we have to deal with long sentences. We gave a sentence of 394 words. Only RASP was able to do something about it. This is the sentence. Okay, this whole thing is a one sentence. All parsers gave up. Partial parse tree came from RASP. Okay, and of course, a very difficult phenomenon is garden pathing. So the old man the boat. If you backtrack only, you will be able to get this structure. The old is the noun phrase, man the boat is the verb phrase, and so on. Then there is this part on dependency parse tree, which I do not have time to cover. Okay, thank you.